Welcome all, TCS seminar at the Wollan University. Today we're happy to have Clément Rambaud, our friend, collaborator from Université Côte d'Azur in Nice. And Clément is going to talk about his big project on k-treedepth and how does it relate to excluding graph minors. Welcome to you.
Thank you. Thank you, Pierre. Okay, so to start, I want to ask a very general question. What is a graph of low complexity? So how can we measure the complexity of a graph? And I will start with just very simple axioms. So first, I want a measure of the complexity of a graph, such that the graph with no vertex, the null graph, is not complex. Okay, I think we all agree on that. So this is my first axiom. My second axiom is that when I add a vertex, whatever its neighborhood, the complexity will not increase too much. Okay, it's slightly more complex, but not too much. So, of course, we could argue that it's not a good axiom. But okay, I will start with this. And now, the third axiom is that the disjoint union doesn't increase the complexity. So, if you have two graphs which are not complex, and then you take the disjoint union, it's not more complex. Okay, so if we have these three properties, we can define the treedepth, which is really the graph parameter given by these three axioms. So first, you have a base case. So the treedepth of the null graph, the graph with no vertices, is 0. Okay. When you add a vertex, you increase the treedepth by at most plus 1. So for every graph G, the treedepth of G is at most 1 plus the treedepth of G minus U. Okay. So adding a vertex for whatever its neighborhood is just at most plus 1. And if you have two graphs G1 and G2, then the treedepth of their disjoint union is at most the maximum between the treedepth of G1 and the treedepth of G2. So this is really free. A disjoint union is free. It doesn't increase the treedepth of your graph. Okay? So what are graphs of small treedepth? So first, there is only one graph of treedepth equal to 0, and that's the null graph, which is here. Okay? Then when you want to build the graphs of treedepth equal to 1, you take graphs of treedepth equal to 0, and you add a vertex on top of it, and you take a disjoint union of what you obtain. So here you will obtain every graph with no edge, okay? Because you take the null graph, you add one vertex, so now you have just one vertex, and then you take the disjoint union, so it gives every edgeless graph. Okay, now when you want to build graphs of treedepth equal to 2, you take something like this, you add a vertex on top of it, so you obtain a star, and you take the disjoint union, so you obtain a star forest. So here I depict only the maximal graphs of treedepth equal to 2, but if you remove an edge or a vertex, it doesn't increase the treedepth. Okay, it's just I depict only the maximum. Okay, so now for graphs of treedepth 3, you take something like that, you add a vertex on top of it, and you take the disjoint union, so you obtain this. It's like that. And you can continue graphs of treedepth equal to 4, etc., etc. Okay? So, so this is good. This is a measure of how complex is a graph, but it's really strong. Graphs of small treedepths are really not complex at all. They are very strong properties. Like this is graphs of treedepths at most t is a WQO for the inducer graph relation. But okay, whatever it means. Okay, you have only very simple graphs in such classes of bounded treedepths. And in particular, you don't have paths. So paths have large treedepths. And why is that? Well, you have a path, and the path is connected, right? So you need to start by removing a vertex. You cannot say, okay, it's the disjoint union of two simple graphs and continue. So you have to start by removing a vertex. But whatever the vertex you remove in your path, you still have a path of length half smaller, which is disjoint from the vertex you remove. So you pay +1 to remove a vertex, but there is still half of the path which is preserved. And so just this argument gives a logarithmic law of 1. So the treedepth of the path on n vertices is at least log n. Okay? So if you have a graph that contains a very, very long path, not induced, just as a subgraph, then you are sure that its treedepth is large. Okay? And something which is very interesting is that the opposite direction also holds somehow. So if you have no path of length L in your graph G, then the treedepth of G is at most L. So this is a long path is a certificate of large treedepths, and if you don't have path of length L, then the treedepth is also at most L. So this is a characterization of graphs of small tree depth somehow. Okay, and so the proof of this is very simple. It's just 3 letters, DFS. So the idea is just that it's enough to decompose every connected component of your graph, because tree depth of a graph is the maximum tree depth of its connected component. And now that you have a connected graph, you choose a vertex arbitrarily, say this one. You find a DFS tree rooted on this vertex, so it gives a spanning tree like this. And now what you do to decompose your graph is that you remove the root. Okay, so you pay +1 to remove the root. Then in every component of what remains, you remove the root again. Okay, so you pay again +1. Then you remove every root of the remaining subtrees, etc. Again, you remove the roots, etc. So here we conclude that the tree depth was at most 5. Okay, and here the point is that, sorry, every time you remove a vertex, you decrease the depth of your trees that you are decomposing. Okay, and so in the end, you show that the tree depth is at most the depth of this tree. But since this tree is a spanning tree, the depth is also has an upper bound, which is the longest, length of the longest path in the graph. Okay, because this is a path, and so if you don't have paths of length L, then the depth of this tree is at most L, and so you conclude that the tree depth of G is at most L. Okay. So the consequence is that a class of graphs C, an infinite class of graphs, has bounded tree depth, meaning that there exists a constant C such that every graph in calligraphic C has tree depth at most C, if and only if there is an integer L such that no graph in C contains PL, the path on L vertices, as a subgraph, or as a matter. Okay, so now I want to, okay, paths are still quite simple in my opinion, so we can try to change a little bit the definition of tree depth so that the paths have small complexity, have small value through this parameter. So here is a possible definition. So this is called 2 tree depth, and it's defined as follows. So again, for the null graph, it's 0. When you add a vertex, you increase by at most +1. So this will be true for every parameter that I will consider in this talk. When you add a vertex, you just increase by at most +1. But the third axiom is more general. So before we had that the tree depth of a disjoint union is at most the maximum between the tree depths of both sides. And here you can do more than just a disjoint union. You can also take 2 graphs and glue them on one vertex. Okay. And here I say that the 2 tree depths of the result is at most the maximum between the 2 tree depths of this and the 2 tree depths of this. So this is again a free operation somehow. Okay, so the null graph is 0, adding a vertex increases by +1, the disjoint union is 3, and the gluing on 2 graphs on one vertex is also a free operation. So we can look at graphs of small 2 tree depths. So there is only one graph of 2 tree depths equal to 0, and that's the null graph. Fine. When you want to build graphs of 2 tree depths equal to 1, you add one vertex on top of the null graph, and you take just the disjoint union, so you obtain every edgeless graph. And now it's different from tree depths, starting at 2 tree depths equal to 2. Because now we can obtain every forest, we have every forest in graphs of 2 tree depths equal to 2, while before we had only a star forest. And the reason for that is that before, at the step before, we had an independent set, so when we add a vertex on top of an independent set, we have stars. And now we can glue stars along one vertex, as many stars as we want along on one vertex, again and again and again. So in the end, we obtain every forest. Okay. And now if we want to build graphs of 2 tree depths equal to 3, we take a forest, we add a vertex on top of it, so we obtain an apex forest. And then we build every graph where the blocks are apex forests. So for example, here you have a block, and this block is one vertex plus a forest. Okay? And every block is like this. And so this is graphs of 2 tree depths equal to 3, and then you continue for graphs of 2 tree depths equal to 4, you add the vertex on top of it, and you consider every graph where a block is one vertex plus something like this, etc., etc. Okay. So now I will start to talk about minors, because actually in all these parameters, the subgraph relation is not enough, I would say. And the real good notion of containment, graph containment, is the notion of graph minors. So, okay, we say that a graph H is a graph of G if you can obtain it from G by removing some vertices and removing some edges. And for the graph-minor relation, you can remove vertices, you can remove edges, but you can also contract some edges. So you take two adjacent vertices, you identify them, you remove the loop and the multiple edges you created, and this gives a minor of a graph. And you can repeat it again and again. So all the graphs that you can obtain like this are the minors of G. And it's very relevant here because if H is a minor of G, then the two treedepths of H is at most the two treedepths of G. This was also the case for treedepths. And okay, so this is one first observation. And another observation is that there are canonical graphs of large two treedepths, and that's ladders. So grids 2 times L grids like that. And I claim that grids like that have large two treedepths. And the reason is that they are too connected. So you cannot start to decompose them by saying, okay, that's two graphs that we glued on one vertex. This is not possible. You have to first remove a vertex. But whatever the vertex you remove, there is still half of the ladder which is disjoint from the vertex you remove. And so you pay +1 to remove a vertex, but you still have half of the ladder to decompose. And so for the same reason as for paths which had treedepths logarithmic in n, here two treedepths of ladders are logarithmic in n. Okay. So now if you have a graph that contains a big ladder as a minor, then you are sure that its two treedepths is large. It's a certificate of large two treedepths. And there is this very nice theorem by Huynh, Joret, Micek, Seweryn, and Wollan, which says that it's an if and only if. So if you have a graph that do not contain this thing of length L as a minor, then it's two treedepths at most some function of L. And so now an infinite class of graphs has bounded two treedepths. If and only if there is an integer L such that no graph in the class contains this 2 times L grid as a minor. Okay. So this is a very nice theorem. I will show you a proof later. And okay, so treedepth is a rather well-known parameter. So treedepth, it's clear. But treewidth is something very, very useful, of course. And there is a very similar definition, actually. So I will define treewidth here as follows. So again, we have a base case for the new graph. So the treewidth of the new graph is -1. Okay, it's for a historical reason. Let's say that we start with -1, but it doesn't change much if we start with 0. Again, adding a vertex increases the treewidth by at most 1. So treewidth of G is at most 1 plus treewidth of G minus U. Okay, so this is just like treedepth or two treedepths apart. But now we have a much more powerful operation, free operation. So for treedepths, we were saying that the disjoint union is free. So the treedepth of a disjoint union is at most treedepths of both sides. For two treedepths, we could also glue two graphs on one vertex. And here for treewidth, we can do what we call a clique-sum. So clique-sum of two graphs G1 and G2, it's any graph that you can obtain by choosing in G1 a clique, in G2 another clique of the same size, and identify them, doing something like it. And you can remove some edges if you want. Okay? And here I say that the treewidth of any clique-sum of G1 and G2 is at most the maximum between treewidth of G1 and treewidth of G2. And actually, this characterizes treewidth. And it's very close to the first definition of treewidth, actually, by Huynh, I think, which was in terms of clique-sums like that. Okay. So concretely, it looks like that. Okay, so yes, you have the three axioms. So graphs of treewidth equal to -1, you have only one of them, and that's a new graph. Good. Graphs of treewidth equal to 0, you have edgeless graphs. Graphs of treewidth equal to 1, you have forest. Graphs of treewidth at most 2, you have things like that. And then you can continue. Okay. So now, what are properties of treewidth? So first, it's monotone for the graph-minor relation. So if H is a minor of G, then treewidth of H is at most treewidth of G. And grids have unbounded treewidth. And grids are really here the canonical examples of graphs of large treewidth. So again, this gives a certificate of large treewidth, because if you have a graph that contains as a minor the L times L grid, since the L times L grid has treewidth L, and since the treewidth is monotone for the graph-minor relation, you know that your graph has already treewidth at least L. And there is a very fundamental theorem by Robertson and Seymour called the Grid-Minor Theorem, which says that that's the only possible obstruction. So a class of graphs has bounded treewidth if and only if there is an integer L such that no graph in C contains the L times L grid as a minor. Okay, so if you don't contain the L times L grid as a minor, then your treewidth is some function of L. Okay. So just to conclude a little bit this overview of these graph parameters, this here is what we have. So we defined the 3 parameters relying on basically 2 axioms plus a free operation. So the 2 axioms were a base case, you give the value on the null graph, so let's say it's 0, -1 for the treewidth. Adding a vertex increases by at most +1. And then you have a free operation, which was the disjoint union for treedepth, gluing on one vertex for 2 treedepths, and any clique-sum for treewidth. And so for each of these parameters, we have obstruction. So what I call obstruction is what you need, what is necessary and sufficient to exclude to have bounded 3 depths, 2 depths. Okay, so that was paths, ladders, so 2 times the grids, and grids. Okay, and now my goal will be to complete this picture, to somehow unify these parameters and to try to fill this table between 2 treedepths and treewidth. So how to do that? I propose to define this parameter. So k here is a positive integer, so it will be between 1 and plus infinity, basically. And the k-treedepth, it's the largest graph parameter satisfying 3 axioms. So you know the first 2 ones. So it's 0 on the null graph. Adding a vertex increases by at most +1 the value of the parameter. And if you take 2 graphs, G1 and G2, and you do a less than k clique-sum of G1 and G2, so less than k clique-sum means a clique-sum, but where the clique has size less than k. Okay, so you choose a clique of size less than k G1, a clique of size less than k G2, and you identify them. Then the k-treedepth of the result is at most the maximum between the k-treedepth of G1 and the k-treedepth of G2. Okay, so this is a free operation. So why it's consistent with what we did before? Because, for example, for k equal 1, what is a less than 1 clique-sum? It's just a disjoint union. Okay, you take a clique of size 0, that you identify with a clique of size 0, so you just have the disjoint union. For k equal 1, clique of size 1, for k equal 2, a clique of size 1, just a single vertex, and so you are allowed to either take the disjoint union or to glue 2 graphs on one vertex, and this is your free operation for 2 treedepths. So indeed, the 2 treedepths is 2 treedepths. Okay. And when you take k being plus infinity, you have no constraints on the size of the clique on which you do the sum, and so you obtain treewidth, or actually treewidth plus 1 because the base case is different, but this is basically treewidth. Okay, so this definition unifies the definitions we have seen so far. And we have the usual properties that it's monotone for the graph-minor relation. So if H is the minor G, the k-treedepth of H is not the k-treedepth of G. So I will only consider the graph containment relation, which is the graph minors. Okay. And now here it becomes more interesting because there are families, canonical families somehow of graphs of large k-treedepths. And this is different from what we had for treedepths, 2 treedepths, and treewidths, where we had only one family, which was respectively paths, ladders, and grids. Here we have several families, which are incomparable. So what are these families? Well, you take a tree T on k vertices, and you consider the family of all its Cartesian products with paths. For example, if you start with this tree, which is a path, then you obtain grids like this. But you can also start with a star on 3 divs, here, for example, and you obtain the family of all the graphs like that. Okay, this is the Cartesian product. And it's not very easy, but not too hard to show that all these families, whatever the choice of T, has unbounded k-treedepths. And this is morally for the same reason as for ladders. Okay, it's not really k-connected anymore, but not too far from being k-connected. And so you almost need to start by removing a vertex, but then half of the structure is preserved, and so you will obtain not really a logarithmic bound, but something close to a logarithmic bound. Okay, so this gives as many families of large k-treedepths as there are trees on k vertices. And the result I wanted to present today is the other direction. So, okay, if you contain something like this for a very long L as a minor in your graph, then you know that your k-treedepth is large. And actually, the other direction holds. So, if there is an integer L such that you don't contain T times PL, whatever the choice of T, tree on k vertices, then your k-treedepth is at most some function of k and L. So in terms of graph classes, it means that the class of graphs has bounded k-treedepth if only if there is an integer L, such that for every tree T on k vertices, no graph in the class contains T times PL as a minor. Okay. So now I would, for the remaining of the talk, I would like to explain you how we can prove something like that. But first, maybe just some illustration of this theorem. So really, for every integer k, positive integer k, this gives a characterization of graph classes having bounded k-treedepth. So this is really one theorem for every value of k, right? Somehow. So for k equal 1, you have only one tree on k vertices, okay, just k1, okay, the graph of one vertex. And when you take the family of all its product with paths, you obtain the family of all the paths. And so you recover the fact that the class of graphs has bounded tree depths if and only if you exclude the path. Okay? So, oops, sorry. Then for k equal 2, you have again one tree on two vertices, just an edge. And when you take its Cartesian product with paths, you obtain ladders. Okay, it's 2 times L grids. And so you recover the theorem which says that the class of graphs has bounded k tree depths, 2 tree depths, if only if it excludes something like this. But now you can go further. You can look at the obstruction for 3 tree depths. So again, there is only one tree on 3 vertices, that's the path on 3 vertices. And so the theorem says that the class of graphs has bounded 3 tree depths if and only if you exclude something like that. Okay, and starting at 4, you have several things to exclude. So now you need to exclude something like this and something like that. Okay, because you have 2 trees on 4 vertices, the path and the star. And so you need to exclude one member of each family to have bounded the 4 tree depths. Okay, and then you can continue, etc. But the title of this talk was excluding a rectangular grid. So can we say something where we just exclude one family, which is the grid of height k? Okay, so you fix an integer k, so this is really fixed, and you fix an integer L. What about the graph that excludes the k times L grid as a minor? So the problem is that they have unbounded k tree depth starting at k equal to 4 because there are several trees on k vertices. And so there is one tree which is not the path. And so this family will have unbounded k tree depth but still excludes your grid. Okay, so it's not true that when you exclude just the k times L grid as a minor, then the k tree depth is bounded. But still it's close to be true because of this property which says that for every 3t on 2k minus 1 vertices, not k vertices, but 2k minus 1 now, the k times L grid is a minor of t times the long enough path. So this means that the k times L grid is always in big enough obstructions for 2k minus 1 tree depth. And so the corollary is that if you exclude just the k times L grid as a minor, then the 2k minus 1 tree depth is bounded. So it's an approximate version of the theorem. And I like to think about it as correspondence somehow. In the Grid-Minor Theorem, which says that when you exclude a grid, the fluid is bounded, somehow the height of the excluding grid corresponds to the size of the clique-sums you have to make. So of course, it's in this very specific setting where you can add a vertex and pay just +1 for it. But this is really the meaning of this corollary, I think. Okay. Now I will try to show you the main tools used to prove this theorem. And okay, so what we want to prove now is the following. If you have a graph G, such that for every tree T on k vertices, T times PL is not a minor of G, then the k tree depth is not some function of k and L. This is what we want to show. The other direction, which is that all the graphs of this form, T times PL, have large k tree depth, is much easier. So now I just want to talk about this thing, which is the other part. Okay, so where these obstructions T times PL appear, actually it's very natural, and the real obstructions are more things like that. Imagine you have k disjoint paths and a lot of pairwise disjoint connected subgraphs, which are the columns here, so that each of them intersect all the k paths, and they are connected. And suppose also that they intersect the k paths one after another. So imagine you have something really like in this picture, but with every colored blob which is connected. Then I claim that you will find an obstruction like this, T times PL for some tree T on k vertices. And the reason for that is that, okay, it's a connected graph. Every column is a connected graph, so there is a spanning tree. now there are only k to the k minus 2 spanning trees. So one of them will appear many times. So you will keep only this one. Okay. And now this is a tree T I will take, and just by contracting some columns that are not used anymore, I will find my obstruction T times PL as a minor if I add enough columns in the beginning. So this is really where this comes from, this obstruction T times PL. The real obstruction somehow is something like this. And the first lemma is a generalization of this observation. So what I was saying is that if you have k-disjoint paths with many pairwise disjoint connected subgraphs, each intersecting all the paths one after another, then I find my obstruction. And this lemma says that you can remove the assumption that they intersect the paths one after another. Okay, so just if you have any family of k-disjoint paths and any family of some function of k and L pairwise disjoint connected subgraphs, each intersecting every qi for I between 1 and k, then you find your obstruction T times PL for some tree T and k vertices. Okay, so it can be complex, it can look like that, or it could be worse. But still, in the end, you will find these obstructions. Okay. So this is not very hard to prove, just quite standard arguments. And it becomes very useful when combined with these very important properties of property of graphs of bounded treewidth, which is the generalization of Huynh property for trees. And it says the following: for every family F of connected subgraphs of my graph G, if there are no d plus 1 disjoint members of F for any integer d, then there is a heating set of size at most d times treewidth of G plus 1 for F. What is a heating set? It's just a set of vertices that intersect every member of F. Okay, so this is really a kind of duality between packing and transversal. Okay? Either I have a d plus 1 packing for my family F, or I have a transversal, a heating set of size d times treewidth of G plus 1. Okay, so why it's useful for us? Well, first, the treewidth is bounded for us because of the Grid-Minor Theorem. Okay, by the Grid-Minor Theorem, if the treewidth is large, then I contains big grids, and I will find I exclude one of the grids, which is the k times that grid. So, okay, just by the Grid-Minor Theorem, I can assume that my treewidth is bounded. Otherwise, I find my obstruction with the Grid-Minor Theorem. And now this thing becomes very useful because we combine with the first lemma by taking F to be the family of all the connected subgraphs intersecting all the paths Q1 up to Qk. Because now this lemma exactly says that this family has packing number at most some function of k and L. And so this says that there is a heating set which has bounded size. So when I combine these two lemmas, it says that in a graph that excludes all my obstructions T times PL for every tree T and k vertices, then any family of k-disjoint paths can be somehow separated with a constant number of vertices. So I can find constantly many vertices, such that every component of what remains is disjoint from one of the k paths I had in the beginning. Okay. So this is how we will use it. And to show you how we'll use it very concretely, I want to show you the special case of the theorem. So we want to show that if we exclude all our obstructions, a tree on k vertices times the path of length L, then the k-treedepth is at most some function of k and L. And as I was saying just before, we can assume that the treewidth is bounded by the Grid-Minor Theorem. And here I want to show you a proof where it's not the treewidth which is bounded, but the path width. Sorry, I didn't define the path width, but the definition is simpler. It's okay. What is a path decomposition first? It's a sequence of subsets of vertices, W1 up to WL. And it's a path decomposition if first every edge lies inside one bag, and every vertex, U, when you look at all the bags Wi containing U, it gives an interval of bags. Okay, that's only consecutive bags. Okay, so this is the definition of a path decomposition, and now the path width is the minimum over every path decomposition of the maximum size of the bag, -1. Okay, so sorry for this very quick definition of path width, but now we can prove this special case where the path width is bounded using this theorem by Robertson and Seymour, which says that there is a path decomposition which is well connected and of minimum width. So the width is the maximum size of the bag -1. And so not only you will find a path decomposition where every bag is small, it has minimum width, but additionally, there is a very nice connectivity property. So this connectivity property says that for every integer k, when I take two distinct bags, either I find two consecutive bags between them whose intersection is smaller than k, and in this case, this gives a cut of size less than k between my two bags. This is a property of path decomposition. When you take the intersection of two consecutive bags, that's the cut between the left and the right side. Okay, and so in this case, of course, you can't find k disjoint paths between the two bags you choose at the beginning. And so Robertson and Seymour says that actually that's the only case where you can find a path decomposition where it's the only problem you can have. So either you find such an adhesion, so the intersection of two consecutive bags of size less than k between wx and wy is the two bags you were considering, or you find k disjoint paths. Okay. So how to use it? So now I have a graph, and I assume that the path width is bounded, and I also assume that it does not contain the obstructions for k-treedepth. So for every tree t on k vertices, t times pl is not a minor of my graph. And my goal is to show that the k-treedepth of the graph is then at most some function of k, l, and the path width. Okay, because here it's a special case where I assume that the path width is bounded. So the starting point is really this theorem by Robertson and Seymour. So I know that there is a path decomposition which is well connected. Okay. So the first step is to identify all the adhesions. So an adhesion is the intersection of two consecutive paths. So I identify all the adhesions which have size less than k. Okay, that's the blue adhesions in this picture. And the idea is that here I will do some clique-sum. So if I can decompose every interval of bags between two adhesions of size less than k, then in the end I will just do some clique-sums along this blue set to obtain my full graph. And I will bound the k-treedepth like that. Okay? So this is, identify intervals where all the adhesions inside these intervals are bigger than k, at this k. And now I apply what I know on my path decomposition. So there are k disjoint paths between the first bag and the last bag. Okay, this is given by Robertson and Seymour. Now I apply the two lemmas I mentioned before. So the family of all the connected subgraphs intersecting all my paths as bounded packing number. So there is a fitting set of bounded size. This is the red set, and I remove it. And now the crucial observation is that, okay, after removing the red set, I also remove the blue set, but okay, this is constant size, so that's fine. And the crucial observation is that now, when I take component of what remains, since it's disjoint from the fitting set, it's not in the family that I consider. And so one of the k disjoint paths is disjoint from the component I want to process now. But by properties of tree decomposition, it means that the path decomposition induced on my component has smaller width than the decomposition I had in the beginning. Okay, because I remove somehow a path from the leftmost bag to the rightmost bag in my interval, and removing such a path decreases the size of every bag by at least one. So now, on every component of what remains, I can call induction. So in total, I obtain something like this. The k-treedepth of my graph is at most 2k minus 1 for the vertices in the blue set that I just remove one by one. Some function of k of l times treewidth of t plus 1, which is bounded by path width of t, for the red set, which is the fitting set I remove in the middle, plus what I pay for the induction. But here I decrease the path width. Okay? And the base case is trivial. If the path width is 0, then you have an independent set. That's clear.
Clément,
yes?
Can you repeat? I just lost track for a second and I didn't recover. So this inequality is 2 times k minus 1. This is for the clique-sum at the end.
Yes.
Why is it 2 times k minus 1?
Here and here you have both sides. Okay. I will decompose, if you want, the torso of this interval. So I will decompose the graph induced by the bags from this one to this one, plus cliques on the blue sets. Okay, and just to ensure that it's cliques, I just remove, I add one by one the vertices on the blue sets.
So on the left and on the right.
Yes, exactly.
And then clique-sum is for free.
Yes.
Okay, so this I understand. Now, now I missed what you do in the. So you remove one path from left to right, or you remove all the paths?
No, I separate them. So I consider the. Okay, maybe I will draw a picture. Right. Okay. So I have my path decomposition that looks like that. Okay, so I have the cliques here, but okay, it's path size in total at most 2k minus 1, so that's fine. And I know by the property of the path decomposition that there are k division paths between the first and the last byte. Okay, so I don't know, it looks like this. Okay, and now I look at the family F of all the connected subgraphs intersecting all my k paths. Okay. Now this family has bounded packing number, otherwise I find the obstruction. This is the lemma I mentioned before.
Yes.
So by the 3D property for graphs of bounded path tree width, and even path width in this case, I will find the heating set with the same color. I will find the heating set of bounded size for this family. Okay? So I don't know how it looks like, let's say like this. Okay? It's a heating set, so it has bounded size, maybe it's a bit misleading. Okay.
So this hits all the connected subgraphs that hit all your paths.
Yes.
Okay.
So now, okay, I pay 2k minus 1 plus the red thing in the middle to remove these vertices. Okay.
Yes.
And now I want to decompose what remains. But now consider a component, a connected component of what remains.
Yeah.
Well, it's disjoint from the heating set, right?
Yes.
So it's not in my family.
Yes.
So one of the k disjoint paths is disjoint from it.
Beautiful. Okay.
And so you decrease, so here, let's say it's a component C you want to process, you want to decompose. Then just the path decomposition induced on this component.
Okay.
Yes.
That's the induction code, but then how do you glue it together with the rest?
Okay, so I have C, which has k-treedepth at most, something which is bounded.
Yes.
I add on top of it all the vertices in my heating sets, all the vertices here. So it's one big clique if you want.
Yes.
And then I do the clique-sum with the other parts, with the other interval that I processed. But here it's a clique because I added it in the end. So.
Can you repeat why the orange thing is bounded?
Yes. So it's because I consider the family F of all the connected subgraph H. I don't want to write it because it's really okay. I can consider it in the full graph actually, such that V of Qi intersection V of H is not empty.
For every I. So this is bounded packing number.
Yes.
So you have a hitting set. And this bounded packing number is
some function of K and L.
Function of K. Because then you want to do the pigeonhole over there. I see. So it's a function of K and L.
Well, it's really properties and that I apply. So there is a heating set of size packing number times 3 plus 1.
Yes. Okay.
So this is how I find this heating set.
Okay, thank you.
Okay. What's the question? Okay, so it's a classic trick, I think, to use induction on path width, and to do that removing a vertex from left to right. And it's something very useful. Okay, so I continue. So now I want to show you the idea of the main proof. Okay, without the assumption that the path width is bounded. Because, okay, here I'm saying it's rather easy to decrease the path width and apply induction, because you just have to remove a path. Well, it's not obvious, but okay, you can do it easily. For true width, it doesn't work. I don't know how to make it work so easily. And so a very good source of inspiration is the proof for k=2, which is already known. And so the proof is as follows. So first, it's enough to consider all the blocks, all the two connected components of your graph, because then you will glue all your blocks on one vertex, and so you will bound the 2 treedepths of your graph. So suppose that your graph is two connected. So choose two vertices arbitrarily. So in the beginning, you can choose them really arbitrarily. And okay, you are in a two connected graph, so you have two division paths between them. Okay. And now I say the following. Okay, I could say by the lemma I mentioned before and this argument, I can separate my two paths, removing a constant number of vertices, but here it's an overkill. I will just apply Menger, between the two paths. So either I find a lot of paths between my two blue paths, something like this, but then an easy application of Erdős-Székely shows that actually you will find your ladder, either like this or something crossing. But in both cases, you will find your ladder. So it's not the case. And so there is a separator between your two paths. So this is really the simplest case of the lemma and this reasoning I was explaining before. But here you have only two paths, so that's much simpler. Okay, so you separate your two paths. So you pay some constants, but you remove some constant number of vertices for this fitting set, for this separator. And now you want to decompose what remains. So again, you decompose into blocks, okay? And now I will just focus on one block, and it's enough because once I can decompose every block, I will be happy. Now there are two observations. First, my block is disjoint from one of the two blue paths, okay? Because I separated them, and now I have something connected, so I cannot intersect both. First observation. Second observation, my graph was too connected in the beginning, so I have two disjoint paths between my red block and the two blue vertices I had in the beginning. And this will be the two new vertices I will choose to start again this argument. So again, there are two in my red block, there are two disjoint paths between the two red vertices, and I can separate them removing a constant number of vertices. And I continue like that. So again, in what remains, I found two disjoint paths inside the red block between my green block and the two red vertices. Here and here, that's the two endpoints of these two paths. And between these two paths, I apply the same arguments again and again. Okay, so what is important to have in mind is that we do this actually in every block, okay, but in parallel somehow. And you continue and you continue. And so now I want to justify that this process will end after a bounded number of steps. Okay, if we can do that, then we are happy. Because the value in the end will just be the sum of this size plus this size plus this size plus this size. And okay, each of these sets, each of these separators have bounded size, and so in total we will bound the tree depth. And why this is true? Because actually we are building a ladder. So here, if you forget about all the cycles, etc., you just look at the black paths and the colored paths corresponding. You obtain a ladder. So every time you go one step further in your process, you add a new step to your ladder. Because here, again, you will consider a block, you will consider two disjoint paths, and then you will find the paths, two disjoint paths inside your block between them, etc. So you will construct one new step of your ladder. And so that's it. If you don't have the 2 times a grid as minor, then after n-1 steps, you will stop. And so your two-tree depth will be bounded. Okay, does it make sense? So this is a beautiful argument. But okay, now we want to generalize this to k-treedepth. And so what is missing? Well, something which was very nice for two-tree depths was that we had the decomposition into blocks, into two connected components, and that's very well defined, very clean. And the blocks are induced a graph of my original graph, so everything works perfectly well. It's not so clear for k-connected components, so we need somehow decomposition into k blocks. So far it's not very precise, but I will come back later to this problem. But actually, okay, we wanted to decompose our graph into blocks because at some point we were saying, okay, I have my two blue vertices, which are somehow roots, and I know that there are two disjoint paths between them. And then I take a separator, etc., etc. So this is why we had to decompose into blocks first. But if we were doing this, I mean, really the root of the argument is that we want to bound the number of steps in our algorithm. Okay. Every time we remove a vertex, we want to guarantee that we are building one new step to our ladder, and so we will not do this too often. Okay, so this is very vague, I know, sorry. But first, okay, before doing more concrete stuff, I need to define properly what is a tree decomposition. I think it's now unavoidable. So a tree decomposition, it's a pair where, okay, so it's a tree decomposition of a graph G. It's a pair where you have a tree and a family Wx for x in V of t, which is a family of subset of vertices of G. And you have two conditions. The first one is that when you take a vertex and you look at all the bags containing its vertex, then the corresponding vertices in T induces a non-empty connected subtree. Okay. So for example, when I take a vertex which is here, then it gives two bags, the blue bag and the red bag, I think. And these two bags induces an edge here, this edge in the tree, and so that's okay, so this is my first condition. And the second condition is that every edge lies inside one bag. So for every edge UV, there exists a bag that contains it. Okay. So this is the definition, and now the width of a tree decomposition is the maximum size of a bag minus 1. And the adhesion can be useful also. It's the maximum size of every edge xy in the tree of wx intersection wy. Okay, so it's the maximum size of an intersection like this. This is the adhesion, and the width is the maximum size of the bag. Okay. So why it's relevant for us? Because it's very helpful to generalize the notion of decomposition into blocks. I know that there are definitions, but you can say that the decomposition into blocks of a graph G, it's a tree decomposition of adhesion at most 1, because between two blocks, you have at most 1 vertex, which is a cut vertex. And every bag will be one block, and so it will be two connected. It induces a two connected subgraph. So this is what I consider the decomposition into blocks. And you can somehow generalize that. So, sorry, I forgot to cite the paper, but okay, it's something also well known now at least. For every graph G, you can find a tree decomposition of adhesion at most k-1, which is well connected. And here, well connected means that for every bag, when I take two sets of vertices of the same size I, which is at most k inside this bag, I can find I disjoint paths between them. So somehow I cannot split anymore a bag. Okay, so this is really a good analog of the decomposition into blocks, but for higher values of k, not just k equals. Yes?
So these paths, they can leave the bag?
Yes, yeah, that's a very important observation. So not in this picture, but yes, in general you have, they are connected in the big graph. So maybe your paths go here and then here. Yes, that's connected inside the big graph, and it will be a problem later. Okay, so this is one observation, and the second observation is the connection of this notion with clique-sums. So the idea is that when you take two adjacent bags, or even if you take an adhesion actually, it will give a clique-sum. So it will give a clique-sum between the left side and the right side, but well, not exactly actually, because you need to be sure that you are gluing your two graphs on a clique. So you can cut on your adhesion, put a clique on this adhesion on the left side and on the right side, and then you can say that my original graph was a clique-sum of this and this. Okay, so usually we say that G is the less than k clique-sum of the torso of every bag, and so the torso of a bag, it's a graph induced by a bag plus some cliques on the adhesions around its bag. This will be also a problem. Okay, so now if I want to bound my k-treedepth, it's enough to decompose, to bound the k-treedepth of each of the torsos of my tree decomposition, because here the adhesion is at most k-1, so indeed that's less than k clique-sums. So a first problem is that a torso is maybe not a minor of the original graph, because you glue clique everywhere. And the problem is that now maybe by using these cliques you have bigger ladders, I mean bigger obstructions. And so you are not sure that your torso excludes all the obstructions, the 3 and k vertices times the path of length L, for example. So this is a big problem. And the idea is that, okay, maybe we can't ensure that the torso is a minor of the original graph, but we can ensure something weaker, which is that the connectivity is not higher. So if you have two sets A and B in your bag, and I disjoint paths between them in the torso, then you also have I disjoint paths in the original graph. So this is something we don't have in the tree decomposition I mentioned before, but this is something we would like to have. Okay, so okay, it's not a minor of the original graph, but the connectivity is not higher, and this will be enough for us because we'll, in the end, build our obstructions using k-division paths and a lot of connected subgraphs intersecting all of them. So if from k-division paths in the torso we can recover k-division paths in the original graph, it will be enough. Okay. So this is the first problem and first half of the solution, but the big problem is that we can't ensure this property. So we can't ensure that every torso is no more connected than in the full graph. But still, we can state another optimistic property, which is false then, but a weaker version is true. So this will be enough, and this is, I think, the right way to think about the problem. Actually, there is a k-lin tree decomposition, so every bag is well connected as before, with an additional property, which is that every adhesion is well connected on one side of the graph, on one side of the adhesion. So when I take two different subsets of my adhesion, I can find a linkage between them only on this side. So I cannot find always a tree decomposition like that, but almost. And the observation is that now if I consider the torso of this bag, and if I have k-division paths inside this torso, then using this property of the adhesions, I can simulate the fake edges I added in the torso using this division path. And so, okay, sorry, it's a bit vague what I'm saying, but believe me, something like that is true, and it will be enough for us. Okay, so this is one problem, which is almost solved. And okay, so a second bigger problem, actually, is that when we were doing the proof for k equal 2, we were just looking at one bag, okay? And we were building at every step, one bag, but one block. And at every step, we were building one new step, for the ladder, again and again. But here, it's not so easy because, as you were saying, the bags are connected in the general graph. So maybe you are building a new obstruction inside your torso, but actually in the real graph, the paths will go outside to come back, and so maybe you will intersect what you were building before in the ladder you will be before, maybe you will now intersecting it with what you are building inside your block. So that's a big problem. And really the worst thing is this thing. So I never realized before this project actually that this is false. It's not true that if you have k-division paths between a set of size Ka and a set of size Kb, and k-division paths between B and C, which is also size K, it's not true that you have k-division paths between A and C. Something which is just not true, and this is a counterexample. And this creates a lot of problems. Because, okay, and here the link with this path that intersect is that maybe you have one step of your ladder here, then you build a new step, and then at the step you build after, you intersect the path you had before, and you completely break your obstruction. So this is really a big problem. And so the idea to solve this issue is to not really build ourselves the obstruction. We will just use the lemma which says if I have k-division paths and a lot of pairwise disjoint connected subgraphs intersecting all of them, then I find my obstruction. Okay, the lemma I used for the caves or the pathways was found. And the way I want to find such a family of k-division paths and pairwise disjoint connected subgraphs intersecting all of them is using a layering. So layering, it's a partition of the vertex set of your graph into subset of vertices that I will call the layers. And the property is that when you take an edge in your graph, either it lies inside a layer or between two consecutive layers. Okay? And now the crucial observation is that if I have k-division paths between L1 and L7, in this example, then this k-division paths must intersect all the layers between, because there is no jump, okay? There is no edge between L3 and L5, so I must cross all the layers between. So if I manage to build a layering like this, which is very long, and if every layer is connected, and if there are k-division paths between the first layer and the last layer, then I find my obstruction. So this is how I will build step by step the ladder. I mean, not the ladder, but the obstruction, so the generalization of the ladder. Instead of really building it ourselves, like in the case equal 2, we'll just build a layering like this, and in the end, we say, okay, if my layering is long enough, then k-division paths between the first layer and the last layer will give me my obstruction. But, okay. There is a big problem, is that a layering maybe doesn't exist, because the number of layers is always at most the diameter plus 1. It's just because when you take a vertex in the first layer and the vertex in the last layer, then their distance is at least the number of layers between, because the path between them must cross all the layers between. And so really the worst case is when you have a universal vertex. Okay? Take any graph, I add a universal vertex, and now the diameter is 2, and so I don't have any layering on more than 2 layers. 3 layers. Yeah, 3. Okay. So this is really a big problem, because I want to be able to decompose graphs like that. Okay, adding a vertex almost doesn't change my parameter, so this is really annoying. And the crucial observation is that when I have a universal vertex, then removing it decreases the tree width. So this is a simple exercise to show that. If you have a universal vertex, then removing it decreases the tree width by at least 1. And so now we come back to our original proof for path width, which was by induction on path width. But now we want to do an induction on tree width using this idea. But it's not very easy to really implement this idea, because okay, here it's really when U is a universal vertex. Okay, if it's not tree universal, it doesn't work. And so to still use this idea, we need to generalize this notion of tree width to a notion of tree width which is focused on a subset of vertices. So this is an idea that is useful for other problems. Some of the people here can talk about that. But okay, so I take S a subset of vertices, and what I will call a tree decomposition of GS. It's a tree decomposition of the subgraph of G induced by S, but with an additional property, which is that when I take a component of what remains, C, there exists always one bag that contains its neighborhood. Okay, so it's somehow compatible with the tree decomposition. Okay, you cannot have a jump between two bags that do not intersect. This is equivalent, I think. Not wrong, but okay.
So wait, you were decomposing only G of S, not the supergraph?
Yes. No, yes, I know I'm doing it. Okay, so you really have a tree decomposition of S like this, and this is exactly S. And when you take a component C of what remains, there exists a bag WX that contains its neighborhood. And so you have components like that which are attached. Okay. And so now we can define the tree width of GS as the minimum width of a tree decomposition of GS. Okay. And the crucial observation is the following. When you take any vertex U, you can take S to be, in this case it's S prime, S to be the union of all the bags containing U. So here the blue vertex is U. Okay, you look at all the bags containing U, and I take the union of this bag, and I remove U. And then I claim that the tree width of G minus U S prime is smaller than the tree width of G, I mean the width of the original decomposition. And just because the picture is here, okay? I take this, just I restrict to this my tree decomposition. This is a tree decomposition of G minus U S prime, but I remove the vertex in every bag, so I decrease the width. So somehow the neighborhood of a vertex has smaller tree width than the original graph. And this is how we will use this idea in the main proof. So, okay. So I think I will try to show you really at a high level the main proof, how to use this idea. So first now we are working not on we don't want to decompose G, but G S prime for some superset of S. So instead of decomposing the full graph, we just want to decompose a superset of S which is given. Okay? And now we want to proceed by induction on tree width GS. And so what we will really do is to prove this, if there is no obstruction of length L, so a tree on K vertices times the path of L, in G, then there exists S prime, a superset of S, that k-treedepth of GS prime is at most some function of K, L of the tree width of GS. And now we can proceed by induction on tree width GS, because we have something more general. And so at some point we'll say, okay, the neighborhood of this vertex has smaller tree width, so I can decompose it. This is really the main idea. Okay. So the first step will be to find a well enough connected to decomposition of adhesion k minus 1. So this is what I mentioned before. So, okay, now imagine that you are in a graph which is k connected, just to simplify a little bit. Because now we just want to decompose the torso of every bag. But okay, let's say the graph is k connected. So to simplify.
Why treewidth is bounded? Because you exclude some planar graph, or what is that?
Yes, exactly. Oh, yeah, sorry. In the end, I take S to be every vertex, V of G.
Okay.
And now treewidth of G, V of G is just treewidth of G, because I decompose everything.
Okay.
Yes?
Yes, I think I missed something, but what is the treedepth of G S prime?
Yes, it's because I didn't define it. No, but it's just you take the inductive definition, but instead of the base case having the k-treedepth of the null graph is 0, you say if S is empty, then it's 0. You stop once you don't have any vertex of S. Does that make sense? Okay. Okay. The idea is that you want just to decompose the superset of S. No, actually, it's slightly different, but okay. Yes, it's very similar to that. Okay, what I'm saying is not exactly true, but there are two ways to define it. But okay, for treewidth GS, you just decompose decompose exactly S, but you don't care about what remains, and you do the same thing for k-treedepth. So yes, you can define it. It's not very hard to define, but that's really the idea is that you will decompose this S, and you have hanging components which are not yet decomposed. Okay. It's just because we want to do an induction on treewidth GS. So the base case is when, for example, when S is empty, treewidth GS is 0 or -1 maybe. But what can we say about the k-treedepth of the full graph? We can't say anything. Okay, it's only about S. So we cannot decompose the full graph directly. We just decompose a superset of S. So it works like that. If I have enough time. Yeah. Okay. So imagine you already built a layering of your graph, and to simplify, imagine that the layers are all connected. So now, since we live in a graph which is morally k-connected, you know that you have k-division paths between V0 and Vl prime, the last layer. So if you reach a very big number of layers, you are sure that you find your obstruction because you find k-division paths and a lot of lowest division subset of vertices, inducing the connected graph that intersect all your k-paths, and so you find your obstruction. So now we want to do an induction on L prime, and but going downward. So when you add something to L prime, you go from L prime to L prime plus 1, you can call induction. So how we do that? So the first thing is to ensure that we will build a new connected layer. So this is really the analog of the argument when we were saying we take two division paths and we can separate them. So here there is something similar, we will not explain, but that ensures that when you take the components of what remains, the layer which is here, which is VL prime minus the component you are decomposing, this thing is connected, and so you are creating a new connected layer. Okay, so you can believe me on that, I hope. You can do that. There are some additional fixes that I will skip. But now we have a problem, okay? We have a component, and we would like to call induction on L prime on this component, just by saying, okay, if all this, so VL prime minus the component I want to process, is a new layer. This is what we want to do. We want to increase our layering and call induction because we have one more layer. But the problem is that maybe we have some jumps between this layer and this layer. Okay, so it's not a layering. And here comes the trick of the induction on treewidth. For every vertex which is here, actually we maintain that there are only a bounding number of them. So for every vertex here, its neighborhood on C prime has smaller treewidth, so I can decompose it, and I do this for every vertex in the neighborhood of C prime on VL prime minus 1. And doing this, I can decompose all the neighborhood of the previous layer. And once I did this, I can decompose all the components of what remains, because now this component will be my last layer. The new VL prime will be everything with VL prime minus the component I want to process, and then the previous layers doesn't change. And so I increase by 1 the length of my layering, and so I can call induction. So this is the very general idea of the proof. You call induction here, and then you combine everything, and in the end you you bound k-treedepth of your full graph. So sorry, it's not very precise what I'm saying. Okay, maybe I will have time to talk 5 minutes more. Okay, so now it's we don't talk anymore about the proof. You can wake up if you want. So maybe, okay, now what I would like to show you is a further generalization of all of these k-treedepths, etc. So the axiom I started with was a base case, the new graph has a treedepth 0. Adding a vertex increases the parameter by at most +1. And we have a free operation. But actually, we could do, in the definition of treedepth, and didn't see other parameters after, we could do something like adding a vertex, then taking the disjoint union, then adding a vertex, etc., etc. We allow any sequence of disjoint union and adding a vertex. And the idea is that if you take any set of allowed sequence of disjoint union, adding a vertex, clique-sum, etc., etc., this gives a new parameter. Okay? Just you are allowed to decompose your graph only using this sequence of operations in this order. And so the definition will look like that. So you consider an alphabet that will describe the operations you are allowed to do. So you have a letter A for apex, for adding a vertex. Okay, so when you read the letter A, you are allowed to add a vertex and paying +1 for it. And you have letters sk for every positive integer k, which says, okay, now you can do less than k clique-sums of what you obtained before, as many as you want. Okay, so formally you can describe it like that. For the empty word epsilon, you obtain a parameter. Oh yeah, sorry. So now for every word w on this alphabet, I will define a parameter pw. So for the empty word, it's 0 on the null graph and plus infinity otherwise. So that's my base case. Now, if the last letter of my word is a, I take the minimum between pw of g, where okay, here I'm including pwa, so I take the minimum between pw of g. So I just skip this letter, and pw of g minus u plus 1 for every vertex u. So if you want, you can remove a vertex, but you can you pay +1 for it. If the last letter is sk, then I take the minimum between pw of g and every possible clique-sum that makes g. So okay, I'll write it like that, but that's really just you're allowed to do as many clique-sums as you want. So this gives a parameter pw for every word w, and now for language L over sigma, you just take pl of g to be the minimum over every word w of pw of g. So, okay, so this is very abstract, but actually it describes very concrete parameters. So if you have the language A star, you can only remove vertices, and you pay +1 every time you remove a vertex. So you will obtain the parameter, which is just the number of vertices. And here the obstructions are just graph with no edges. Okay, a class of graphs has only graph of bounded size if and only if it excludes every graph in the class excludes an independent set like that. Well, it's pretty trivial. Now, when you take A star S1, you can build graphs of bounded size and then take a disjoint union. So it's the maximum size of a connected component. And here the obstructions are stars and paths. It's easy to show again. Now something more interesting, when you take AS1 star, then you can do any sequence of vertex addition, disjoint union, vertex addition, disjoint union, etc. So you obtain the treedepth. And the obstructions are paths. But you can play with it. So for example, you can consider AS1 star, so treedepth, but then add S2. And then it's the maximum size of the maximum treedepth, sorry, of a block of your graph. Okay, you build graphs of bounded treedepths, and then you glue them on one vertex. And here the obstructions are cycles. It's something known. It's not completely trivial, but it's known. So the parameter I studied is the k-treedepth. So it's a language A sk star. So you add vertices, you do less than k clique-sum, you add vertices, etc., etc. And so the obstructions are like this. And you can also introduce a new letter, which is just a shortcut. So s plus infinity, which is all the letters sk. So you can make clique-sums of arbitrary size. And then the treewidth, okay, either you put s infinity in the definition of k-treedepth, or you can also write it a star s plus infinity. And in both cases, it gives treewidth +1. So the obstructions are great. It's Robertson and Seymour Grid-Minor Theorem.
So the star shouldn't be in brackets after.
You have two options for treewidth. Either you build cliques and you do clique-sums, and that's the end, or you can allow to add vertices in the middle, but it doesn't change anything for treewidth. But where it will change something is when you fix the size of the clique-sums. So when you are allowed to add a vertex at any moment and then do a clique-sum, etc., it gives k-treedepth. But if you do clique-sums only in the end, you obtain k-treewidth, which is the minimum width of a tree decomposition of adhesion at most k-1. So for example, for k equal 2, it's the maximum size of a block, etc., etc. And the obstructions are known. It's in a preprint by Huynh and Joret. And the obstructions are more complex to describe, but okay, for k equal 2, that's things like that, k2t and cycles. And you can also have much more classic parameters like vertex over number. It's AS1 A star, because A, you have one vertex, AS1 independent sets, and then you add vertices on top of it. And so you count how many vertices you need to remove to have an independent set. So that's exactly vertex over number. Plus 1 because you have the vertices in the end. And you also have a feedback vertex set, for example. So here you build first A square, so it's an edge. A square, S2, you build every forest. And A star, you add vertices on top of it. And so it counts how many vertices you need to remove to obtain a forest. And so here the obstructions are the joint union of triangles, that's Robertson theorem. And so there is this very complex general problem, which is given a language over sigma, can we characterize graph classes having bounded PL in terms of excluded minors? So this is quite complex probably, but something which is more concrete is it true that there are finitely many families of excluded minors? So it's probably true, it's a very special case of a much more general conjecture. And, oh, there is no thank you, but okay. You can imagine thank you and that's the end. Thank you.